If you could travel back in time to the early stages of the solar system, some 4.5 billion years ago, you wouldn't simply find the one life-friendly world you'd expect in the form of planet Earth. Instead, there would have been three worlds with similarly life-friendly conditions: Venus, Earth, and Mars. In terms of the physical conditions they possessed, all three of them looked very similar from a planetary perspective, as they all had substantial surface gravity, copious amounts of volcanic activity, and atmospheres similar to Earth's in thickness and pressure. They all possessed volcanoes, watery oceans, and complex interactions between the surface, oceans, plus clouds and hazes, enabling these worlds to retain significant amounts of the heat they absorbed from the sun. Moreover, at these very early stages, even the compositions of their atmosphere were similar, as they were all rich in molecules like hydrogen, ammonia, methane, nitrogen, and water vapor. For a time, conditions were favorable for life to potentially arise on all three worlds, and indeed it may have arisen on all three at some point in the distant past. However, on all but one of these worlds, it didn't last. Venus experienced a runaway greenhouse effect, boiling its oceans away and rendering it inferno-like after only a few 100 million years. Mars lasted far longer before becoming inhospitable, perhaps as much as 1.5 billion years. These are the stories of how our planetary neighbors met their respective demise. It's remarkable that worlds that, today, are so different from one another might have had such similar histories in their early stages. It wasn't just Earth, but also Mars, that likely experienced catastrophic early collisions, with Earth's creating our moon and Mars's creating three moons, the largest of which likely fell back onto Mars at a later date. The remaining two Martian moons, Phobos and Deimos, as well as Mars's severe asymmetry across its two hemispheres, are two of the key pieces of evidence that support this ancient impact theory for Mars, with similar stories occurring on icy, moon-rich worlds like Pluto as well. Venus may have suffered an impact that altered its axial rotation severely, but remained a moon-free planet. What is certain, however, is that all three worlds, Venus, Earth, and Mars, were definitely shaped by both external impacts and internal geologic processes, as mountain ranges formed atop extensive highlands, great basins stretched across dramatic lowlands, rift valleys formed, and volcanic activity, including lava flows, covered the surface. All three possessed molten, liquid interiors, leading to incredible amounts of volcanism, adding both volatiles and carbon dioxide to the atmosphere and creating relatively smooth seafloor bottoms. The water that was both expelled from the planet's interiors by this activity, as well as water brought to the planetary surfaces by impacts, would become planet-wide oceans, completely covering the lowest elevation areas. When you compare Venus to Earth to Mars, however, there are three major differences that leap out at even a casual observer: their orbital distances from the Sun, the rate of their planetary rotations, and their physical sizes. That first factor, the close proximity of Venus to the Sun, likely sealed its doom from a very early stage in planetary history. Although Venus is 95% the size of Earth, and the Venus-Sun distance is 72% of the Earth-Sun distance, that latter figure translates into Venus receiving approximately double the energy from its parent star that Earth receives. Of course, back in the very early days of the solar system, the Sun was much cooler and less luminous than it is today, emitting just a fraction of the energy it does at present. Over time, however, all stars heat up because as they consume the nuclear fuel in their cores, the core grows, heats up, and the rate of fusion within them increases. Over enough time, the star's temperature and luminosity increases as well. In the early stages of our solar system's history, this may have created initially life-friendly conditions on Venus. Once the planetary surface becomes cool enough to solidify and to enable liquid water's presence upon it, The same life-friendly conditions that eventually led to the emergence of biological activity on Earth may have been at play on Venus as well. But unlike Earth, Venus's close proximity to the Sun meant that as the Sun's energy output began to increase, Venus began to get hotter from its surface to the top of its atmosphere at a much greater rate than the outermost worlds. As an incredibly volcanically active planet, the water vapor spewed up into Venus's atmosphere certainly helped retain heat emitted by the planet and also absorbed from the Sun. These dual effects didn't just heat the planet, but a hotter planet resulted in a greater rate of evaporation at the planet's surface, which further increased the amount of water vapor present in the atmosphere. It didn't take long, from a planetary perspective, for this to lead to what we call a runaway greenhouse effect, where increasing temperatures create conditions that cause the planet's temperature to increase even further. After as little as 200 million years, but perhaps up to several hundred million more, Venus's surface became hot enough that any liquid water on its surface would inevitably boil away. From a planetary perspective, it never recovered, because it's located at a much greater distance from the Sun than either Venus or Earth. Mars encountered what can only be described as the opposite problem to Venus. Mars is much smaller than Earth, at barely half the size, but it orbits more than 50% farther away from the Sun, meaning it receives only 43% of the energy input per square meter that we get here on Earth. With such a low amount of incident energy arriving, you might think that liquid water would have been impossible on such a world, particularly when the Sun was much cooler, and that Mars would therefore be destined to be eternally frozen. Fortunately for us, we can be confident, beyond a shadow of a doubt, that this wasn't the case. There's tremendous evidence for copious amounts of not only past liquid water on Mars, in the form of sedimentary rock, hematite spheres, dried-up riverbeds with oxbow bends, canals that appear to flow into large depressions like valles marineris, etc., but of current liquid water as well. Down the slopes of crater walls, although the claimed detection is contested by some, we've observed from orbit what appears to be evidence of water flows, which leave briny deposits behind in their wakes, even today. The full suite of evidence we have teaches us something profound about the early conditions on Mars. Even early on, there must have been a substantial Martian atmosphere, creating a strong greenhouse effect on that world, enabling sufficient temperatures and pressures to maintain liquid oceans, rivers, and lakes on the surface. There must have once been, early on, much greater surface pressures on Mars than its current thin atmosphere is capable of creating. And that atmosphere also had to do a phenomenal job of trapping the Sun's heat. Without those conditions in place, early Mars would have been a frozen world, something that the evidence definitively contradicts, as the past evidence of liquid water is simply too great and compelling. Such atmospheric conditions on Mars are not possible today, unfortunately. The Sun emits a constant stream of charged particles known as the solar wind, and they're constantly smashing into the Martian atmosphere. Because its surface gravity is so much lower than Earth's, it's easy to knock particles found in the atmosphere off of Mars and into the abyss of interstellar space. Thanks to NASA's Mars MAVEN mission, we have even measured how quickly Mars is losing its atmosphere today, and can draw conclusions about how quickly the process of atmospheric stripping would have transformed a once Earth-like atmosphere into Mars's modern atmosphere.